This video is about groups of tables or individual tables that are guaranteed to feature in any BS7671 18th edition exam on the wiring regulations. Understanding how to use the tables will give you confidence and help to improve your exam score. Because some tables are grouped together, there are actually more than 10 tables, and a couple of calculations are included as well. All good practice, and do follow the worked example questions, which of course include the answers. This is a selection of tables from parts 4, 5 and 6 of the Wiring Regulations book that often appear as questions in the BS7671 18th edition exam. And this video uses the 18th edition Amendment 2 book, the Big Brown Book. Amendment 3 was released as a supplement in 2024. Download and attach the Amendment 3 supplement to make your Amendment 2 book Amendment 3 compliant. Amendment 3 is available as a free download from the IET by following the link in the description to this video. Tables 1 is a group of very important tables that always feature in an exam. They are to do with earth fault loop impedance, shortened to EFLI or just ZS. This group starts with table 41.1 on page 65. What is the required maximum disconnection time for a particular type of circuit? What is the voltage range of the circuit? Is it a TNCS, TNS or TT earthing system? Take note of the less than and the less than or equal to symbols. In the example in the red box, U0 is greater than 120 volts and not more than 230 volts. A domestic final circuit attached to the national grid might measure 240 volts, but its nominal voltage U0 with reference to the zero earth potential is 230 volts. Think of nominal as a name that we call it, regardless of what it actually measures. Always use nominal voltages for these tables. A domestic circuit will not fall into the 230 volt to 400 volt band shown above, and the symbol for nominal voltage is always pronounced U0. A typical exam question might ask, what is the maximum disconnection time for a TNCS domestic final circuit with a nominal voltage of 230 volts AC? Find the voltage range for 230 volts nominal, find AC, and find TN for TNCS, and read off the maximum disconnection time. And the answer is 0.4 seconds maximum. Now that we know the required disconnection time, we can look at the maximum permitted earth fault loop impedance, or ZS, for different types and ratings of breakers and fuses. Table 41.2 on page 67 is just for fuses, and specifically for fuses that must meet a 0.4 second disconnection time as required in many final circuits. Read the table heading. Do not get confused with 5-second disconnection times, which is a different table. Again, a question. What is the maximum permitted ZS for a 230 volt domestic final circuit protected by a 20 amp BS88-3 System C fuse? Remember, in an exam, for a final circuit, assume 0.4 seconds disconnection time. Follow the red boxes above, and out comes the answer of 1.93 ohms. Table 41.3 on page 68 is different. This is for the maximum EFLI or ZS for circuit breakers and RCBOs with a maximum disconnection time of 0.4 seconds and 5 seconds for final circuits and distribution circuits. Both are covered in just one table. Look at this typical exam question. What is the maximum permitted earth fault loop impedance for a distribution circuit with a required disconnection time of 5 seconds that is protected by a 32 amp Type B BS7671 circuit breaker. Find Type B, find 32 amp and read off the maximum ZS of 1.37 ohms. Back to fuses now, and table 41.4 on page 69. This table is for 5-second disconnection times for distribution circuits. Do not confuse this table with table 41.2. They look similar, but the answers are different. Here's a question. What is the maximum permitted ZS for a 230 volt distribution circuit with a required disconnection time of 5 seconds that is protected by a 20 amp BS88-3 System C fuse? Find table 41.4, find BS88-3 System C fuses, find 20 amps and read off the answer, which is 3.2 ohms. For the same fuse rating, a longer disconnection time will allow a higher maximum ZS. Compare this answer to the same fuse in table 41.2. Table 41.5 on page 70 is for the maximum ZS for circuits relying on RCDs for protection, where the circuit breaker cannot achieve the required ZS, typically in TT earthing systems. But where does 1667 ohms come from, you ask? If you take the touch voltage of 50 volts, which is the upper limit for AC extra low voltages, and divide it by the tripping current for a 30 mA RCD, we have 50 volts divided by 0.030 amps, which is 1667 ohms. A question for us. The measured ZS for a 230 volt AC TT earthing system exceeds the maximum permitted ZS for the MCBs installed and relies on an RCD with a rating of 100 mA for circuit protection. What is the maximum permitted ZS in these circumstances? And the answer is shown above, 500 ohms. Please note that you cannot just declare that all your circuits will now have a maximum ZS of 1667 ohms just because you have RCDs or RCBOs installed. You must still attempt to achieve the correct ZS figure given in the previous tables. This table should be used where overload protection cannot be achieved by circuit breakers or fuses, and all other means of reducing ZS have not achieved a low enough ZS. For example, reducing the length of the circuit, changing the MCB or fuse for one of a lower rating, or changing the MCB for a different type, for example Type C to Type B. Table 41.6 on page 74 is to do with 55 volt single phase and 63.5 volt 3-phase circuits. It covers circuit breakers and fuses and is a simple cross-reference table just like the others. Question. A 6 amp BS EN60898 Type B circuit breaker protects a single phase circuit with a U0 of 55 volts AC. What is the maximum permitted earth fault loop impedance for this circuit? Follow the red boxes and we have an answer of 1.74 ohms. Table 2 is about temperature limits of accessible equipment, a popular table for exam questions. Look at table 42.1 on page 91. If someone is in close proximity to hot equipment or needs to handle such equipment, what is the maximum temperatures to prevent burn or injury? Just decide how the person might touch that part, then decide if it is a metallic part or a non-metallic part, and read off the corresponding maximum temperature in the last column. Let's answer this question. A non-metallic part that is intended to be touched in normal use but not handheld must not exceed what temperature? And 4 choices as you will find in an exam. Read the answers carefully. Some questions will include Fahrenheit as a possible answer when the regulations book will always give temperatures in Celsius. Exam setters will often do this to see if you are paying attention. The answer is 80 degrees Celsius, answer choice number 4. Moving on to table 3, we have K values and the adiabatic equation for time. K is a factor for how fault currents affect certain common materials. It is the material factor of the cable. We are most often interested in 70 degrees Celsius thermoplastic insulation and sheathing with a copper conductor size of less than 300 square millimeters, as in twin and earth cable. This has a K value of 115 as shown. An exam question might ask, what is the K factor for 90 degrees Celsius thermosetting cable with copper conductors? Find thermosetting, find the column for 90 degrees, and where the copper conductor row coincides, read off the answer. This has a K value of 143. The table for K values on the previous slide also leads us very nicely to another common exam question, the adiabatic equation for time, which uses the K factor. This is regulation 434.5.2 on page 98. T equals K squared times S squared divided by I squared. The adiabatic equation for time shows us the time taken for a conductor of a certain size to reach its limiting temperature with a stated fault current flowing through it. Let's have a look at an example question. What is the time taken, T, for a 4 square millimeter copper conductor in 70 degree Celsius thermoplastic sheathing to reach its limiting temperature if the K factor is 115 and the fault current I is 800 amps? Shown here is the calculation, and we can see that the copper conductor will reach the limiting temperature for the cable of 70 degrees Celsius in 0.33 seconds. If this circuit was a final circuit with a maximum disconnection time of 0.4 seconds, the MCB or fuse may not operate before the limiting temperature was reached and cable damage may result. We should consider increasing the CSA of the conductor, which will increase the time. Try it for yourself with, say, 6 square millimeter cable and see if you can get the same answer as me, 0.74 seconds. The MCB will trip before the limiting temperature is reached. Table 4 is about the rated impulse voltage of equipment. Look at page 108 and table 443.2. UW is the impulse withstand voltage. If voltage surges are present on the electrical supply system, what amount of overvoltage must certain types of equipment be able to withstand without presenting a danger? The table shows us how much overvoltage in kilovolts that a particular piece of equipment is required to withstand. It shows the different categories of equipment, 1, 2, 3 and 4, and examples of equipment in those categories, and shows the nominal voltage ranges of different installations. The table is easy to follow as long as you read the headings for the columns. Make sure you are looking at the correct category. Here's a question. What is the required impulse withstand voltage, UW, for a 230 volt AC domestic washing machine? Make a choice from the 4 possible answers given. A domestic washing machine is a domestic appliance, so category 2 applies, and the voltage is 230 volts AC. The table shows 2.5, but 2.5 watt. This is where some people go wrong. Look at the top of the table where it shows that all answers are in kilovolts or kV, so choose answer D, 2.5 kilovolts. On to table 5, the separation distance between power and signal cables. This is table A 444.2 on page 122, and this table is different. We should imagine it as 2 separate tables, one table for voltages and another table for amps, and what we do is look for the worst case scenario to find our answer. Try this question. What is the minimum separation distance between a power cable and a signal cable if the power cable carries 100 amps at 240 volts? Find the separation distance for 240 volts, which is shown as 0.45 meters. Then, the second table, find the distance for 100 amps, which is 0.6 meters. What is the worst case? What is the biggest distance required? This is 0.6 meters, and that is our answer. Table 6 is about the minimum cross-sectional area of conductors. Find table 52.3 on page 148. This is nothing to do with how much current is flowing, how much the voltage drop is. It is just how physically small is acceptable as a conductor given the type of material for the conductor and what it is used for. Will it break? There are 4 easy steps: the type of wiring, what the circuit is used for, and the conductor material. Is it copper or aluminium? And then read off the minimum size. A typical exam question might be: a domestic power circuit that is wired in a sheathed twin-earth cable with copper conductors should have a conductor cross-sectional area of not less than, and the answer is 1 square millimeter. As already mentioned, for this question, ignore other considerations such as maximum current, voltage drop, etc. Just answer the question from the table. Device function and coordination tables are the subject of Table 7 group. Look at page 191 and Table A53.1, a very simple table and very useful. It answers the question: what can a circuit breaker be used for? What can an RCBO be used for? And this table will often appear as an exam question. The X's indicate what type of device it is, what the BS numbers are, and then the last 4 columns indicate the functions that the device performs. Question: an RCCB can be used for, and 4 possible choices are given. Our answer should be choice B, residual current protection, as shown in the table. A useful exam tip: all of the above is not always the correct answer in an exam. The second table in this group is Table A53.2 on page 193, device coordination in low voltage installations, where to find the regulations that give guidance on device coordination so that the correct device trips first in the event of a fault. Normally, we want the device that is closest to the fault to trip first so that power is not lost to all the house. Decide what the coordination type is that you need information on, and the table shows you the regulation to look at for this guidance. Look at this question. Guidance on selectivity between RCDs can be found in regulation number and then 4 choices to select from. We should choose answer C. Another exam tip: in an exam, do not waste time checking the actual regulation. Just answer the question from the table and move on. You only have 2 minutes per question. Now for number 8, another group of tables. What is the minimum CSA of buried earthing conductors? Starting with Table 54 on page 198, we can see that there are only 3 easy steps needed to finding the minimum cross-sectional area for a buried earthing conductor. Decide on the level of protection against corrosion, and do the same thing for mechanical protection. Decide on the type of material, copper or steel, and then select the CSA of the earthing conductor. If the question asked, what is the minimum cross-sectional area for a buried copper earthing conductor that has no mechanical protection and is not protected against corrosion? Find the appropriate row for corrosion, find the correct column for mechanical protection, and where the 2 cross, we can select an answer. Select copper or steel, copper in this case, and we have an answer of 25 square millimeters. The table we've just used leads us to the adiabatic equation for size, or CSA, of an earthing conductor. This almost always comes up as an exam question. This is regulation 543.1.3 on page 199, and the equation is shown here. The equation tells us that S, the size of earthing conductor, is equal to the square root of I squared multiplied by T and then divided by K. It tells us that the minimum cross-sectional area S for a conductor will not exceed its limiting temperature before the time T has expired. What minimum cross-sectional area S of copper conductor should be selected if it is not to exceed its limiting temperature before the time T given the following data? There are 4 possible answers. Choose the correct one for minimum size. The box on the right shows the correct calculation in several steps. The minimum size, according to the calculation, is 3.57 square millimeters, and the nearest choice that is not less than 3.57 is 4 square millimeters. This is the cross-sectional area that we should choose. Answer C. There is another method of selecting an earthing conductor size. This is shown in table 54.7 on page 201. It is called the tabulated method because we find the answer in a table and not by calculation. There are 3 rows to choose from. The top row is highlighted here. If S is not more than 16 square millimeters, then the protective conductor is the same CSA as the line conductor. For example, 6 square millimeter line and a 6 square millimeter protective conductor, or CPC. The middle row in blue shows us what to select if the line conductor S is more than 16 square millimeters but not more than 35 square millimeters. The protective conductor is 16 square millimeters, just one size. For example, 25 square millimeter line and a 16 square millimeter protective conductor. For the third row, if S is more than 35 square millimeters, then the protective conductor is half the CSA of the line conductor. So we would have, for example, a 50 square millimeter line and a 25 square millimeter protective conductor. Table 9 is about symbols used in luminaires. An easy table to use is all pictures. Go to table 55.3 on page 224 and take a look. An exam question asks you to identify a luminaire symbol from the wording of the question, as in this example here. The symbol to use for a luminaire with a limited surface temperature is, and 4 symbol choices are shown. Which one matches the words? Easy. Just take each symbol in turn and read the wording that goes with it. Here we have symbol A as the correct answer. Another tip for exams: in an exam, do not waste time analysing the symbol explanations. Find the symbol, answer the question, move on. And on to table 10, insulation resistance. Almost guaranteed that you will have a question on this table in most exams. Table 64 is found on page 234. An exam question will give you the nominal voltage of the circuit under test, 230 volts AC, 400 volts AC, etc. If the question just says domestic dwelling, then assume 230 volts AC nominal. The middle column tells us the test voltage to apply. Note that the test voltage is DC current, not AC. Having selected the nominal voltage and the test voltage for the circuit, the rightmost column will give the minimum insulation resistance for that circuit, given in megohms, millions of ohms. Last question. A 24 volt AC self circuit is to be insulation resistance tested. What is the test voltage to be applied to the circuit under test? And 4 choices. The answer, as shown in the red box, is 250 volts DC. Answer choice D. A common type of question trick here, where AC and DC are both included as possible answers, or for some questions there will be a mix of ohms and amps to see if you are observant. Before we go, there is a very useful section at the back of the book called Table of Tables, beginning on page 573, and some of the tables are highlighted here. These few pages list all the tables shown in the Brown Book in order of appearance. It will give you the table number, the title of the table, and most usefully, the actual page number. It is found immediately before the index. Thank you for watching. It really is appreciated, and I hope that you found this video useful. Please subscribe to our channel to get access to all of our videos, and remember to click on notify to be sure of not missing our next video. And don't forget, you can also type in Learn Electrics into the YouTube search bar to go directly to our channel at any time from any computer or smart device. We are constantly adding new videos to our channel, so don't miss the next one. And once again, thank you for watching, and we hope to see you again very soon.